We're going to be solving problems 13 and 14 from chapter 9. First, we're going to have to find the centroid along the x-axis. The best thing to do when approaching this problem is to draw out the situation so it becomes a little bit more easy to understand. So now we're just going to add in an element. It is going to have a width of dx, and it is going to be represented by y2 minus y1, and the distance from the origin along the x-axis is just going to be represented by x. Now that we've done that, we can set up our integral to solve for the area. So here our area is going to be the integral from 0 to L, which is just the length, of y2 minus y1 dx. Because the top edge is just a straight line, we know that y2 is going to be 4 meters, and since we know the curve of the other line, y1 is going to be 4 minus 1 over 16 x squared. The length is also just given, so we know that's 8 meters, so plugging everything in, we find that the area is the integral from 0 to 8 of 4 minus 1 over 16 x squared dx. And if we go through and we solve this integral, we find that the area is 32 over 3 meters squared. So now we're just going to get rid of everything because all that we really need is the value of that area to find the centroid along the x-axis. To solve for the centroid, we're going to say that it is equal to 1 over the area times the integral from 0 to L times xc dA. And in this particular situation, we can just say that x is equal to xc, and that they're the same value because it's just the distance from the origin to your element. So as you can see here, we are just proving that that conclusion is true. So saying that x equals xc, we can say that the centroid is equal to 1 over a, which is the area, times the integral of 0 to b of x, y2 minus y1 dx. Since our length is still just given as 8, we can say that this centroid is going to be equal to 1 over 32 over 3, as it was our solved area, and then times the integral from 0 to 8 of x, 4 minus 1 over 16 x squared dx. And if we go through and we solve this whole integral and multiply it all out, we find that it is equal to 6 meters. Now we can get rid of all of that and move on to problem 14 from chapter 9, which is the same situation, but instead of finding the centroid along the x-axis, we are looking for the location of the centroid along the y-axis. So this centroid is going to be equal to 1 over the area, which is already solved for, times the integral of yc dA. Now with the y, it gets a little bit more complicated than on the x-axis, so we're just going to redraw the situation so that we can understand what values to plug in where. So we're going to have the same element, it's going to have the same width of dx, and it's still going to be represented by y2 minus y1, except instead of finding the distance across the x-axis, we're going to go vertically on the y-axis, and so our yc value for that distance is going to be y1 plus y2 divided by 2. So using these values, we can say that yc is equal to y2 plus y1 over 2, which is equal to 4 plus 4 minus 1 over 16x squared. And we also know that dA is just going to be equal to y2 minus y1 dx. So using this, we can begin to set up our integral, and it's going to be 1 over the area times the integral from 0 to L of y2 plus y1 over 2 times y2 minus y1 dx. So if we plug in everything that we know now, we can set up the final integral that we have to solve. And that's going to be 1 over the area, 32 over 3 times the integral from 0 to 8, because 8 is still our given length. And then it's going to be the integral of 4 plus 4 minus 16x squared all over 2 times 4 minus 4 minus 1 over 16x squared dx. And if we go through solving this whole integral and multiplying it all out once again, we find that our centroid along the y-axis is equal to 2.8 meters. And this is all that you have to know to be able to solve problems 13 and 14 in Chapter 9. I hope this helped. Thank you for listening.